Okay, hello, everybody. Welcome to the September meeting of the Howard Astronomical League, our monthly meeting for September. We have a pretty good agenda tonight. We have an excellent speaker. I'm very excited to hear about some of the lunar geology topics, and I want to say moon rocks, but I know that's oversimplifying. Yeah, welcome. Let's see if I can figure out how to change slides now. Now what's happening? Oh, there we go. Okay, so our agenda tonight, we will have some introductions and announcements, and then our featured speaker, and then Jim Tomney, who hopefully will make it. He's got some other things going on early. We'll talk about what's out in the sky this month, and there's some exciting stuff coming up. I'm excited about this comet that's coming up that Jim's going to talk about. Might be a really good one. And then we have Arjun, who is going to talk about his trip to India to an observatory, and we'll go through some pictures and wrap it up. So, is there anybody new in the room that would like to introduce themselves? Yes, go ahead.
My name is Alex, and I want to be an astronaut when I grow up, and I'm here to learn about some stuff.
Cool. That's excellent. You picked the right place to be. We'll talk a lot about things in outer space and science and all that stuff. And I don't know if you're aware, but next month our speaker will be an actual bona fide astronaut.
Yep.
So that would be pretty cool.
We're registered for that.
Okay, excellent. Glad to hear it. And Papa?
Yeah, and I'm Chris. My wife Jennifer is also signed up, and we've attended some of the virtual ones, at least one or two, but this is our first time being.
Okay, welcome. Are you on the C-Star list?
We are, yeah.
Okay, great. We can talk about that afterwards. I got the C-Star there, and I have some more stuff in the car. So yes.
Hi, I'm Tom. I'm new to HAL. I just actually bought my first telescope this past week, so
Awesome.
I'm looking forward to it.
Welcome. Have you been a HAL member very long?
Probably less than a month.
Oh, okay. Brand new to HAL. So great. Welcome. I think we'll find that if you just bought a telescope, this is a great club to be in, because there's a lot of people who have a lot of experience with amateur astronomy, and hopefully you can make it to some of the events. The impromptu and members star parties in particular have lots of opportunity to sort of share and gain knowledge, share knowledge with other people.
Yeah, I'm looking forward to it. It's something I wanted to do for a long time.
Great.
Well, welcome.
Welcome, yeah. Anybody else?
Tommy Bell, I'm just returning. I've been on a hiatus for a while.
Okay, well, welcome back. I'm glad you're here. Okay. Yeah, I think we'll just go ahead and move on and to some announcements. So first off is our schedule of star parties. We just had a recent one that was quite a success. I'll talk about it in the next slide. But on the 14th, this last weekend, we had a public star party. And there were a couple of impromptus in the last month as well. Impromptus occur when the weather's nice, we don't have anything on the schedule, and somebody in the club who has, we have a number of people who have keys to the observatory, to the park, to the park and to the observatory. And so if the weather's nice and it's somebody's free, they can just say, hey, I'm going to open up if anybody wants to come out. And so those are good opportunities to share and to get some, practice with your equipment and all that good
You
stuff.
might want to mention if you're a member and you're not seeing that, it's a separate list that you have to sign into.
Thanks, Bill. Did everybody hear that? If you are a member and you don't get the impromptu emails, the ones that notify you of when the impromptus are going to occur, then go on the website and look for you can sign up for that email list on the website. Okay, other upcoming events are, we have another members star party scheduled for the 5th. And then the next public star party is a few weeks after that in October. If you want to get out and view right now, if you get some clear weather, Andromeda is is rising in the east, and that's always a good object. That'll probably be a really good object for the sea star. So, okay, we'll move forward. So speaking of HAL parties, we just had our September public star party. And we had 23 HAL members show up with their telescopes and set up in the parking lot in various locations. We had we had a few different people count. By some accounts, it was 250s, but I think the consensus was we had over 300 people show up that evening. Some of the highlights were that Crystal once again brought her activities tent. You can see that in the picture there, and basically it's lit with red lights, and she had activities for kids, lunar lander challenge, some light bright, make your own constellations, great educational stuff. She's by profession a teacher as well, science teacher. Bob Savoy was there with his solar system as usual. Dale Gemp was in the observatory sharing all sorts of good views. We had Grace with her electronic scope. Phil was out there with 300 power. He had the little eyepiece and his refractor and was zooming in on the craters because it was International Observe the Moon Night. And then they had the big telescope out too. So it was quite an event and it was a lot of fun. I hope you and the weather was fantastic, except for there was some high level smoke that was obscuring the deep sky stuff. But fortunately, the moon and Saturn were out and were still very impressive. But the temperature and the evening was a very nice evening. Okay, so the next thing on our agenda is the book of the month. We normally have Crystal tell us about a book that she has read this past month. She couldn't make it tonight. She's doing something with her students. So I put in a slide for her, and I'm calling it the book of the next month. And this is the book right here. It's actually quite pretty. It's got a lot of very, very nice pictures. And the author of the book, astronaut Tom Jones, will be speaking at a joint event between HAL and the Maryland STEM Festival and the Howard County Public Libraries. If you've seen or received the emails, you're aware that next month will be a special club meeting. So I have my book here, and I was hoping that Ken would be here because I got to figure out how to give this to somebody to ask him to sign it. I'm not going to be able to make the meeting. I have a work trip on the so
Victor,
Victor,
you're going to be meeting with Jim anyway, right? For the handoff of the meeting, Zoom stuff and everything, right?
Yeah, I'm probably going to get with you, Victor, before that meeting. I'm not going to be comfortable just walking into it cold. So you can give it to me. And then for a very small fee, I'll have him sign it for you.
Thank you.
That's
Appreciate
good
it.
because I was going to charge a big fee.
See?
I'm glad you're on, Jim. I'm glad you were able to get here.
Me too.
So yeah, great. That's fantastic, Jim. Yeah, I think it'll be good to have a little dry run over there since all the. Okay, great.
Victor, can I add something? for
Yeah,
the new
please.
people? So for the new, for anybody online, for the new people, in the observatory, we have a library. And for members, they can check out anything in the library. There's a form inside a folder that's right there. And so all the books, we have over 300 items in the books and all kinds of stuff in there. Some of it's very historical. And so it's just available at no cost. You just, when the observatory is open, you go and check it out. And then Crystal's our librarian and she'll make sure you get it back.
Yeah,
So,
it's very informal.
yeah.
We got a comedy section. That one's hysterical, but most of it's historical. Okay. So anyways, if you I'm looking forward, or I was looking forward to reading it before meeting him, but yeah, this looks like it's a beautiful book, good coffee table book. Okay, so moving on to our agenda, without further ado, I would like to introduce, oh no, I should not introduce her because I don't have her slides ready. Phil, talk about the sun. What's going on with the sun lately?
So the sun is continues to be extraordinarily active. We're still in the solar max phase. And this is one of the this is certainly the busiest cycle in the years that I've been studying the sun. I've been doing it since 2012. So there's a lot of activity as far as coronal mass ejections, X-class flares that are part of that. And for solar observers, it's fantastic. It's been with an incredible number of sunspots. For people who are responsible for keeping our satellites functioning, GPS, the space shuttle, the space station, and whatever, it's kind of been tough, with all the storms and stuff. There's a lot to do, but it's just been magnificent. One of the cool things, it continues to be the solar probe that's up there. That's
Parker?
going through. What's that?
Parker
Parker
Solar.
Solar Probe. Thank you. And that's the first man-made object to actually go and touch the sun's corona. And so there's some incredible video on the NASA site as it's been hitting it. So, and it's the fastest spacecraft ever to leave Earth. The speed's traveling, and it's just unbelievable. So there's all kinds of stuff. I encourage you to look at the NASA website and go to that mission.
Has to be fast, that close to the sun,
It's fast.
in order to survive.
Yeah, and you gotta wear like number 40 sunscreen.
Yeah.
But it's amazing.
So the internet is not doing so great here. It's taking its time downloading the file.
Yeah.
Maybe we could, oh, it's a big file. Oh man, it's taking its time.
Or if you have a
No.
USB-C connector, I can go with USB-C.
How many megabytes is it? We're up to 66 megabytes. Oh, we're almost there then. Okay, very good. It's done. Sorry for that, HAL members. Let's see what happens here. If, can anybody see the presentation from Dr. Valencia?
Yep.
Okay, great.
Yep.
So I'll just flip for you if that's okay.
Sounds great. Well, thank you all so much for having me here tonight. We got this connection going because my Girl Scouts are earning their space badge, one of their space badges this year. And so I reached out because we're going to be going to the November 9th star party. And so we've started a wonderful connection here. So today I wanted to talk to you a little bit about lunar samples because I thought that you might not have had a chance to hear too much about the actual samples. I know that Ernie Wright is among your members and no one can top him in visualizations of the moon, so I'm not going to try. We're going to look at samples instead. So I work at NASA Goddard Space Flight Center, but I'm an employee of the University of Maryland. So today my title is Past, Present, and Future of Lunar Sample Analysis. So a little bit more about who I am. I am a lunar petrologist. That means I study how rocks form on the moon, and which means pretty much I have the coolest job in the world. I really can't complain. Besides all the emails, can't complain. Just a couple exciting days I've had. In that top right image with me there in the right, we're each holding up little samples of the moon that were going to be studied. And then down here in the right, that's me there in pink. And in the gentleman with the tie on is the only geologist to ever walk on the moon, that is Jack Schmidt. And what we were doing there is projecting the landing site, the Apollo 17 landing site in 3D. And he was walking us around to talk to us about the different things he did while he was on the moon.
Wow.
So most days really can't complain. It's a great thing to do. Next slide. But what do I actually do besides, hang out with astronauts on the very rare occasion? So I study lunar samples in several ways. First, I'm very lucky I get to work with the Apollo samples. I work on Apollo 12 samples, Apollo 17 samples, and I think I've got some Apollo 15 coming down the line, maybe some 14 too. So I get to study the rocks that we've been carefully preserving for the last 50 years and try and understand their chemistry. That's really, I'm an applied chemist a lot of the time. I spend my days looking at spreadsheets of the chemistry on the micrometer scale within these rocks. We also have a lot of lunar meteorites that I study. So we get a lunar meteorite because something has hit the moon, knocked a piece of the moon off, and that's fallen down to Earth. And they are picked up in desert environments. And we'll talk about more about those later. The last thing I do is mission work. I work on using the Lunar Reconnaissance Orbiter cameras. Next slide. Which are cameras that have been orbiting the moon since 2009, and they are so incredible that you can see the astronauts. So what we're looking at here is the Apollo 15 or 17 landing site. And you can see in this lower path, that's astronaut footprints. And in the upper path, that's the double lines in the upper part there. That is the tracks from the lunar rover.
That was Arjun Schmidt's mission, wasn't
That was Schmidt and Cernan, yep.
it? Yeah.
Schmidt and Cernan. And so every day is something fun to study. Next slide. So first I want to walk us through what we've learned from the Apollo program. And I know that my timing is terrible, given that it was just International Observatory Night, but I would love to be able to give you all a little bit of some tidbits of things to talk about with people. Apollo is one of the biggest ways that people are connected to the moon. And so that's often what people want to discuss is the Apollo program. So I'm hoping to give you all just a little bit from each mission so that you have some knowledge going forward of
For next year.
right, so things to talk about with people in the future. All right. So not to be cliche, but since the dawn of humanity, the moon has been our constant companion. Problem was before the space race, we really didn't know too much about it. We knew what we could look at with generally with the naked eye, and then of course after the advent of telescopes, we could see a little bit closer, but we really didn't know much. And remember that the moon tidally locked with the Earth, which means we until the space race, we had not seen the far side of the moon. So we knew really relatively little. We knew that there are broad swaths of light regions, broad swaths of dark regions. Go ahead.
I have a question for Victor. We
Yeah.
can't see the shared screen or the speaker.
Oh, you're kidding me.
No.
Yeah, change your share screen.
I was seeing slides.
By the way,
You're-
Yeah, I was seeing slides too.
I was seeing slides,
Super informal, just let
What
me
do,
know if you have
what do you
questions.
see now?
the slide.
Slide.
More
The
questions.
slide just
Okay,
came
great.
up.
Yeah. It's been fine. Me. I don't know.
Are we
Yeah,
okay
I see the
now?
slide. Yes, we see the
Yeah.
slide now. Thank you.
Great.
Your camera
Sorry
isn't
about that.
muted on the speaker.
Okay, no, that's great. All right, before the Apollo program and the space race really spurred this momentum to learn about the moon, we really have a lot more questions than answers. And today you could argue we still have a lot more questions than answers about the moon, but we know a lot more than we did. We didn't even know before the space race and before Apollo if the moon was a primitive body, meaning did it have a core mantle crust? Or was it all essentially one composition all the way through? We knew so little about the moon, we didn't even know if it mirrored our own layering that we see on Earth. We didn't know what the broad swaths of mare, the dark regions, were made of. It could have been impact melt from all the giant, the giant basins around the moon. The circular regions are formed by impact that were later infilled by the mare, but we didn't know what that was. We didn't know if it was impact melting from the impact itself. We didn't know if they were volcanic or if they were somehow like a fluffier ash flow. Like you see in terrestrial volcanoes, you often see these big ash flows. And that was one of the hypotheses. We didn't even know how the moon formed yet. We didn't know if the Earth-Moon system formed by capture, meaning the moon was another planetary body that came close to the Earth and it just got captured. That was the best going theory we had, which we now know is not how the moon formed. Another really big issue that scientists were serious and engineers were seriously concerned about was would the landers and astronauts sink into the surface? We did not know if the surface was compact enough to support the weight of the landers and crew. So luckily, everyone could breathe a sigh of relief after we pulled it off the first time, and knew that we were at least safe to explore.
Yeah, we actually did that when the first unmanned lander.
Yep.
Landed on there.
Mhm.
And that was a big, I remember that.
Yep.
Press. And there was another big controversy with the pre-Apollo. I think it was by the time Apollo started, it was probably settled. It goes back a century or more. Were the craters mainly volcanic or mainly meteoritic?
Mm-hmm.
So Patrick Moore was on the volcanic side until he had the evidence collapsed around it.
Yeah, it's there. So like that just points out, we didn't even have the basic knowledge that we take for granted that we know about the moon, like the moon is covered in impact craters, were not well known. And again, pointing out, we didn't even know it was on the other side of the moon before the space race.
When was the cheese theory? Yeah,
Good question. Yeah.
I'm sorry.
Oh, no, you're good. You're good. Right. So everything changed with the Apollo program. We brought back this incredible sample collection that just revolutionized our understanding of the moon. In total, we brought back 382 kilograms of samples through the lunar surface. You can see you were looking at sample mass on the y-axis and Apollo mission on the x-axis. So we had a consistent increase in sample mass with each mission as the missions got more complex and we got better at doing this. So what that means is they collected 2,196 documented samples over 80 hours of exploration of the lunar surface. We found igneous rocks, metamorphic rocks that are formed from impacts, but no sedimentary rocks like we have on Earth. No sandstones, that kind of thing. So we learned that the moon is a very, very different place from the Earth. What? So what this, went back one. What this has yielded for the past 50 years is there have been over 3,200 sample requests put into NASA's curation facilities, and they've allocated over 50,000 subsamples of these rocks for geologists, biologists, material scientists, engineers, doctors, and astronomers to unlock the secrets of not just the moon, but the solar system as a whole, because the moon preserves the record from our early solar system. Go ahead. So what did we learn from Apollo? First, Apollo 11, we got 2 new minerals that we did not know about. They've since been found in terrestrial rocks, but at this point where we did not know about them. The first being armalcolite. Armstrong, Aldrin, Collins, armalcolite. The second one, tranquilityite, along the same lines here, named for the Sea of Tranquility where they landed. So we learned very quickly that the lunar surface is actually ancient and pervasively affected by impact processes. So that goes back to the impact versus volcanic. We learned that the craters are impact. And we learned that the mare are volcanic and have distinct differences in chemistry compared to the basalts that we see on Earth. It's quite easy to tell the difference between a lunar basalt and a terrestrial basalt. The chemistry is very different. And we learned that right away as soon as we brought these samples back. And it was kind of fun. You know, this is a field where these samples were brought back and my entire field was born. I still work with the pioneers who brought these samples back. And so it's interesting. It's a very, very young field. So we may have a lot of questions still, but we've only been at this for about 50 years. So there's still a lot of work to do. Next slide. So what I want to do now is walk through each mission and give you a little bit of background of what is one of the highlighted findings that they learned from that mission. So we'll go over each of these. You can go to the next slide. So the first one, in Apollo 11, they found the mineral anthracite, which led to the development of the lunar magma ocean process. Next slide. And this is where we learned that the moon is a complex differentiated body, which means we know that the moon started as a molten ball. Okay, we call it the lunar magma ocean. Next slide. And then what happens as out in space, things cool down. So the lunar magma ocean begins to cool. And what happens is that as a magma cools, it forms minerals. Some minerals are denser than others. Different mineral structures like to take in different elements. So lighter, less dense minerals floated toward the top of the magma ocean, and more dense minerals sunk toward the inner part of the moon, which is the same thing that happened on Earth, right? We have a metallic inner core, then we have a mantle and a crust. The same thing happened on the moon. We have a metallic inner core, a mantle, and a crust. The difference is on the moon, the crust is preserved. You can go to the next slide. So right away from Apollo 11, we knew that we had we knew that we had preservation of the lunar magma ocean, the crust that had originally formed. We call it the primordial crust. Apollo 12 is my favorite. This gave us the magic component, or the cryptic component, is what they called it when the samples were first came back. What they noticed is the chemistry of these rocks was different than anything that had ever been seen on Earth, in the Apollo 11 samples. Something was new and different. Next slide.
Can I ask
Yeah.
a question on the last? So when did that happen? The primordial crust solidified?
Very early. So no one has it must have done it on this date, because the physics start to get complicated and dating the rock starts to get complicated, because it is because everything's so affected by impact. But it was probably the oldest rock we have dated is 4.46 billion years.
Cool.
So it was somewhere right in that, probably 4.5, but when it was solid enough to be called the official first crust, it is a good question.
No question.
Yeah.
As you're going through, so for what you learned from the Apollo 11 mission, did you learn that, your predecessors, because you were really young before the time to know. So, did they learn about that LMO hypothesis before in Apollo 12, or it came much later?
No, it was immediately after the samples came back.
Really?
They started, and actually go to the next slide, and this is a good periodic table. That's what I need. These elements down here,
Yep.
Those are the rare earth elements. The Apollo 11 samples have a dip in uranium, a very sharp dip. Sorry for those online, you can't see what I'm doing with my hands. But when you plot all the rare earth elements, everything follows a constant pattern. Minerals take in different elements, right? And most of these samples from Apollo 11 had a very sharp decrease in europium, which we know is complementary to the mineral plagioclase, which takes in europium. Plagioclase is what made up the vast majority of that flotation crust. So we learned that must have happened because everything else is missing the europium. So the europium had to go somewhere. And that's the really fun part about doing geology, is we can look, like chemicals are reliable tracers of the processes that these rocks have underwent. So this happened billions of years ago, and I could go in the lab today and look at the europium in a rock, and I can tell you what. So it's really fascinating. And so the rare earth elements really came into play though at Apollo 12. So again, this is that bottom row that's removed from the periodic table. We always just ignored it, right? It's one of my favorite things. But they called it the magic component when these rocks came back, because they did not know what was going on. Some papers call it the cryptic component, and it took a while for everyone to freeze, realize everyone was finding the same thing. and figure out what was going on. So, what this is an elevation in elements. We call it creep now. So K for K for potassium, P for phosphorus, and the rare earth elements are the REs. So we put it all in there, creep. And it also takes elements like thorium, uranium. We call these incompatible elements. They're elements that don't really like to go into crystal structures super easily, of the early formed minerals that the moon was making at the time. So this came back. We found it in the soils in Apollo 12. That's these little black rocks. They were impacty soils that they first found it in, as well as the coolest rock that came back from the moon. That's sample 12013, and I wrote my dissertation on it. And so it was the first rock that they brought back, and they were like, something's different. So it's a pretty fascinating sample. And now we know that this cryptic component or magic component, which we just now call creep. So we talk about our creepy rocks all the time. Geologists love a good joke. So this is a map of thorium on the right. This is from Lunar Prospector, a mission that was in the 90s. And so we can see thorium is one of it's not in the name creep, but it's one of the creep elements. We can see on this map of thorium that some regions of the moon are higher in thorium than others. And so this was not localized to Apollo 12. It's a global, really not global, but it is a widespread feature on the moon. Next slide. So how did this happen? We're coming back to this chart. So now we're all the way to the right. We've got this anorthosite flotation crust. That's got all the plagioclase in it. That's all of our less dense minerals. Our more dense minerals are sinking down. They are forming the mantle. And in the middle, you're cooling from the top and the bottom. And cooling until you're left with a thin layer. Every element eventually has to go into a mineral, whether they like it or not. So when you are cooling a rock and you are almost completely cool, things just start getting shoved into the crystal structure, whether they fit well or not. That's where our creep elements came. And so what we know is that we had a layer in the moon. We don't know if it was global or if it was only on the near side, but we had a layer in the moon that was really rich in these creep elements. So and it's a feature unique to the moon. Any evidence of such a layer on Earth would have been long since destroyed.
Did they have to drill to find them?
Nope. Nope.
So they're like on the side of a hill or something?
No, so we've never sampled a discrete layer that is creep. It has pervasively impacted the chemistry in the region. So it's going to be below the crust. So any volcanics that come up through that are going to assimilate some of those elements. Any sort of large impacts are going to have worked it in. So the whole region, it just has this creep signature to it now. Next slide. Okay, so that's my favorite mission. But on to Apollo 14. Apollo 14 dated the Imbrium impact. That's one of the most important things they did. You can go to the next slide. So Apollo 14 did not land at Imbrium. So why were they trying to date the impact if they didn't land there, right? The Apollo 14 mission landed at the Frau Mora formation, which is south of Imbrium, but it is like the Imbrium ejecta. So when you have a large impact, or when you have an impact on any scale, material is thrown out away from the crater in predictable radial directions. And so Apollo 14 went to Frau Mora to try and to get samples that would have been inside the Imbrium basin and sample them.
Possibly not coincidentally, that was where Ranger 7.
Yep.
First coastal Ranger.
So then something funny happened when they went on the mission. So this is their starting point here, kind of where that cluster, where the lines converge. Then they headed off toward Cone Crater up there in the upper right. The point was to sample along as they went, because the closer to the crater they sampled, the deeper they were sampling. So the rocks predictably go deeper, and are sampled from deeper as you approach a crater. the way the physics of cratering happens. It was a law that we already understood. So the crew walked and walked. They were trying to get to Cone Crater to take a picture inside. And what happened was they went as far as they could and they were exhausted. The terrain was much more challenging than predicted. And they gave up here. And they never saw inside Cone Crater. They were about 20 meters, 20 to 30 meters from being able to see into that crater. And they did not, they thought they were just too far away. They couldn't figure out why they weren't already there because they thought they were supposed to be there by then. And so what they did was they turned back. It was initially thought that they might not have met all of their sampling objectives then to sample as deep as possible and to date that embryo crater. But they did. They met all the objectives, and we now know that that basin is almost 4 billion years old, dated at 3.9 billion.
I had a question for you, not related to geology, just what you were talking about, the astronauts. So was it that they were exhausted and that's why they didn't go that extra few feet, or was it they did the math that if they stayed too long, they didn't have enough oxygen to get back?
So they were, it's kind of a combination of both. So when they landed in Apollo 14, they thought the terrain was going to be really smooth and easy, walkable. And they had this caddy dragging behind them with the tools in it. And it just turned out to be a lot more of a physical effort than anticipated. And they thought they were going to be, they thought they'd already reached the rim. So at least once, maybe a couple times. And then they just weren't there yet. We just weren't there yet. And they were fatigued. And the decision was to turn back because it was getting hard to tell like how much further it really was going to be. Were they going to be fooled again by the next ridge, or should they, turn back then? And so it was a combination, but the crew was absolutely exhausted at that point. And, I'm sure disappointed when they realized how close they really were. But they met all their sampling objectives. They just didn't get to enjoy the fruits of their labor and really see into the beautiful sight that would have been that crater. Next slide. Now, Apollo 15 found something we call the Genesis rock. Next slide. And I'm just going to let you watch it happen. And then we'll talk about it a little bit.
Is it supposed to play automatically or?
I don't think so.
There you go. Click on that. Maybe. No,
No.
slides. Click on the slide one, right there. No.
That's a camera. It looks like just it went in as a picture.
No, it went in as a movie. I tested it.
I'm sorry, I don't know how to do it.
So what's happening is now that we knew that we had that flotation crust, that really impacted our science questions as we move forward in the missions. And one of the things that Apollo 15 was looking for was some of this early formed crust. That's what they wanted to find.
So share that screen.
Yeah.
And so what happened was the crew is walking along and Dave Scott gets really excited. "Oh, I think I found what we came for," because he's seen a brighter white rock on the surface, and that flotation crust type rock would have been brighter compared to the rest of the surface. Yeah. That rock is not the oldest rock from the moon, but it was the oldest at the time, and it was what we were looking for. So they called it the Genesis rock. It was the most ancient thing that we had. Oh, there we go.
It was a security setting.
Ah, okay.
I don't see it.
Was that him or somebody? I didn't see it.
We're not seeing it.
Yeah, we're not, we're-
So while he's working on it, so you can hear, oh, it's all plaids, I'm seeing twinning. So that's a testament to how well
Just share
trained
that screen.
these men were.
We
They-
didn't see the video.
They were not geologists. We sent one geologist to the moon and it wasn't until Apollo 17. The rest of them were trained before they went. And they had about the equivalent of a master's degree in geology before they went to the moon. And you can hear them on the surface talking about the features that a geologist would be describing in the rock when they see it. And they are completely correct in what they saw. They found the Genesis rock that they were looking for. And it might not be the oldest rock we have from the moon, but it does tell us a lot about that time and what the environment of the moon was like then.
Are you guys seeing the screen now?
we are now.
Apollo 15 finds the Genesis rock? Yes?
Yes,
I'm just-
hit play.
We don't have take enough time to watch the moonwalks anyway.
Can you see the video now?
Yep.
Yes.
Yeah, something's moving.
Oh, sorry.
Oh, you're good. So it was quite an exciting find. And there on the right, that's Dave Scott in front. And I think that, so one of the crew was Dave Scott, and that's Erwin, I think, in the back there. And that would maybe be the other crew member. And
Yeah,
then
you can tell who's the commander by the red stripe. And that's Dave Scott with the red stripe.
So what they are there in the Lunar Receiving Laboratory, which is where the samples were brought back and looking at their efforts. Yeah.
And what was it about this rock that stood
It
out?
was the oldest rock that was found at the time. It's since been surpassed in age, but it was what they went to try and find a piece of that original flotation cross on the moon. Because we had already known about it from the previous Apollo missions. And so we wanted to, but we hadn't directly sampled it. And so they wanted to see if they could sample that rock type. And so that's what they went to find. And then they used that crew training they had spent months undergoing, and they identified it on the surface, found exactly what they were looking for and brought it home. All right, next slide.
Scrub on. I'll click here.
Oh, maybe. There we go. All right. Apollo 16 went to a completely different region than the other types of other missions had gone to. Go ahead to the next slide.
How do we know that rock that they found wasn't from a meteor?
So one thing that we can do is we can look at the iron and manganese in rocks, and we can tell which part of the solar system they come from. And so it was all of the chemistry of the rocks tell us it's exactly what it's supposed to be on the moon. We have not definitively found any piece of any other planetary body on the moon. But interestingly, they do find asteroids on Mars. The rovers have found more than one asteroid on Mars. So Apollo 16 landed in the lunar highlands, those big white parts of the moon, right? A lot of people thought that those might be volcanic regions, and what they found is that it was a lot of really broken up rock, and that the whole lunar surface is really, really affected by impact, which means a lot of the rocks that we have are what we call breccias, which means it's a rock that has been broken up, and multiple different types of broken up rock have been thrown back together and fused back together from the heat of impact or compaction. And so Apollo 16 just really drove home the point of how complicated lunar rocks are. Next slide. And then perhaps one of the most scientifically valuable missions was the Apollo 17. It was the longest mission. And they brought along geologists, so that kind of helps things. And we'll go to the next slide. We're going to watch one more video, and you can just hear the excitement in their voice. And after we can talk about how exciting or why they were so excited.
Everybody online see the screen, the orange soils?
Yes.
Thank you.
Now, don't do it until I see it. It's all over.
That's Jack Schmidt.
Don't do it until I see it. I turn it up with my feet. I can see it from here. It's boring. It's real. There it is. Great. Not a big difference.
So he said you told him he had to do this fast. They were out.
Just about 102. It's almost the same as the LED pixel on my camera.
Is this where tan comes from?
We're 10 minutes.
Tan? You'd be old to get that joke.
So I think I gave you 102 or something like that.
But it was invented from.
You know what tan is? Yeah, you said.
Yep.
Television, I'll think that whatever you want to settle on the moon.
So he was just about to say it's been oxidized. All right. And so do we know why Mars is red? Tell me.
I think it's because of like I think it's the atmosphere. Maybe it's like the sun.
Atmosphere, right? When we have things that have iron in them, rocks, a cast iron pan, whatever it is, we rust red. So Jack has seen this on the surface. He's a trained geologist. He sees this on the surface and he's going, oh my God, we have oxidized lunar surface. throw out everything we've just learned, what is going on? And so it was an extremely exciting time on the lunar surface and in the science back room. There's when there are surface missions, there is a back room of scientists helping make the science decisions. And it was a very exciting time, and they were completely wrong. So if we go to I have another picture of it later. You can kind of see it in that one. I have a color enhanced one later. I don't know. I don't think I have another picture on it right now. But what they found is actually volcanic beads that just happen to be orange because of their chemistry. It's not some sort of oxidized soil. What it is fire fountain styling pyroclastic deposits. So that's what we see like in the beautiful pictures that you'll see of like a Hawaiian volcano where lava is just absolutely spewing out and forms tiny little droplets. So that's what we found here is a huge deposit of these little glass deposits or glass beads that form from this kind of a volcanic eruption, which we did not yet know happened on the moon before Apollo 17. So a little disappointing that we didn't suddenly find where oxygen had oxidized things, but next slide. All right. So what are we up to these days? You can go another one. We now know so when we did the Apollo program, we had mapped the moon with images. The precursor missions took some images of the moon. But what we didn't really have is a global perspective of the chemistry. And so what we now know through orbital missions and looking at samples is that we have different chemical regions of the moon. We have this prosolar creep terrain, which is a lot of the lunar near side, which is where most of the Apollo missions landed. This is a chemically anomalous region of the moon where we have those elevated creep elements, the potassium, phosphorus, rare earth elements, thorium, that kind of thing. Then we have the feldspathic highlands terrain, which is our ancient primordial crust. And then we have the South Pole Incan Basin, which is the largest basin in the solar system, and we didn't even know about it until because we had not seen the far side of the moon until the first surveyor went around. And the exact year is escaping me. But we did not know about it, and no human had ever seen it with their own eyes until Apollo 8. Next slide. So now we have all of these new discoveries in old planets. So this is a color enhanced image of what Jack Schmitt was so excited about at Apollo 12. He says this is the close approximation of what he was actually seeing on the lunar surface. So it was enhanced to what he remembers it being. And this is what it looks like in microscope. So what it actually is these tiny little glass to orange beads, and some of them are black as well because they've started to mineralize. And we've studied these samples for 50 years, and about 15 years ago, our analyses were able to get more precise. And what we learned from this sample is that the moon has a lot of water. Or not a lot of water. We used to think it had no water, and now we know it has a little bit of water. And so we are learning more and more every day about the composition of the moon. So we know that there must have been some water in the interior structure, which we don't have oceans, so it's not a lot, but a little bit. Next slide. We also have had the advantage of gaining the lunar meteorite collection. The lunar meteorites, we found the first one in the late 70s, and now we have 649 named stones, and they totaled, what was it? 1,159 kilograms compared to the 382 that are found. So the meteorite collection is really extensive at this point. You can see they're found mostly in northern Africa, but we found some in a few other places as well. Antarctica has found some. Yeah.
And we know they're meteorites because their composition is similar to what was. So if they were found, if there was no Apollo missions, would we have determined that they were lunar meteorites, or would we have just said these are strange rocks? Or
well, we know what meteorites are from Mars, and we know what meteorites come from Vesta, that kind of thing. So we're able to make estimates of the chemistry, and pinpoint where other meteorites come from. So I think we would have been able to figure it out by looking at the chemistry, what's expected throughout the solar system. So the great thing about the lunar meteorites is they theoretically represent the global composition of the moon. The Apollo program only landed in a small region of the moon, right? So the meteorites have given us access to samples from all around the moon. And so they've been a really valuable resource and since they've been found several decades ago.
So how much energy is required for an object to hit Mars and dislodge something that would send it all the way to here?
I don't know that number off the top of my head. I have looked at
I
it.
spoke to somebody at NASA about that same question, and they said, no, the lunar or the Mars meteorites are not from Mars. They're not from the surface. They're floating around in the orbit of Mars, and they get dislodged out of the orbit.
But they were on the surface of Mars, and then they were brought up to maybe orbit Mars and then begin their return journey. But
No, there's not enough energy from anything that hits Mars to send something that high.
Escape energy from Mars is too high.
No, the samples are from Mars. They represent volcanic rocks that are from the Martian surface.
Okay,
Okay, so next slide.
but by the way, if somebody has their hands up online, can somebody just sort of let me know? Because I can't see the Zoom screen at the same time as what I'm seeing here.
So this is that kind of global perspective that the lunar meteorites give us. I won't bore you too much with all the in-depth chemistry, but what you're looking at on the x-axis is the amount of iron, and on the y-axis is the amount of thorium. So the colored in regions that are labeled A11, A12, etc., those are where the Apollo missions, their soils fall. But all of the blue squares are the compositions of the lunar meteorites. And this hasn't been updated for several years, so we will have added to this since. So just to give you a quick look at how we have really expanded our knowledge of what's on the moon based on the ever expanding set of lunar meteorites. And it's very hard to tie them to a specific crater on the moon. So that's where you get into the challenge, right? So now we know we have a global representation of the chemistry, but what we don't know is where everything came from. So some folks try really hard to tie specific meteorites to specific craters and try and narrow down where they came from. But it's really hard to demonstrate that with definitive certainty. Next slide.
I have a question about the collection of the previous slide where you had the number of meteorites collected on the Earth's surface.
Yeah.
So is this because we're just, there's more people out there collecting them, they're sending them for analysis, we know what we're looking for, why are the numbers greater?
It's a lucrative business, and meteorite dealing is very popular right now. And so there's just a lot more interest. There's a lot more people getting out into the desert in Africa, trying to find these things because they're worth quite a bit of money.
Okay, thank you.
Yeah, so all of these were here before 1980.
I'm sure they were. I'm just curious why. Yeah.
Right. Yeah, we're just finding them now.
Yeah.
There has never been a meteorite fall, meaning someone has seen it enter the atmosphere. We've never been fortunate enough to pick up a fall. So you can go.
Yeah, they say that the people in Egypt from a long time ago had a collection of meteorites.
Yeah, especially the ancient Egyptians were especially used the iron meteorites to make daggers, that kind of thing, for royalty. So I want to take a couple minutes to talk about volcanism on the moon because this is what I actually study. So I just want to tell you a little bit about my work. 17% of the volume of the moon is, or the volume of the surface is Mare basalts. These are the basalts like we have all over the ocean floor. So when you pick up a really black rock on Earth and you know it's a volcanic rock, that's a basalt. That's what's all over Hawaii. It's here, it's all over the place here. It's all over the place in almost all of that dark region. What you're looking at is basalt. We also have another kind of volcanism on the moon. We can produce granite or rhyolite, which have the same composition. It's just that they cooled underground or erupted to the surface. So I'll call both of those silicic volcanism. So you can go ahead and turn the slide, and that's what one of the samples looks like, that little white piece. We have about this much granite from the Apollo missions compared to a lot more of the basalts. So, okay, so what exactly are these silicic rocks? We are looking at here, geologists love to talk about the amount of silica in a rock. So we're looking at silica on the x-axis, and on the y-axis, sodium and potassium. The thing I want you to see on here, you can ignore all of that top part. We have a lot of basalt, which has pretty low silica, and we have rhyolite, which is the same thing as granite, and that has a lot of silica. On the Earth, we have all of these things. Okay, on the moon, we have those two, and maybe there might be some evidence from orbit that we could have that stuff in the moon. The important thing is on Earth, we use these middle rocks to make our really silicic rich rocks, our really silica rich rocks, through crustal recycling plate tectonics, right? On the moon, we don't. You can go to the next slide. We have so many silicic rocks on the moon. We make our countertops out of granite. We make our buildings out of granite. We have an abundance, but on the moon, we just have a little bit. So why do we have so much on Earth? It's aided, the formation of granite is aided by plate tectonics and water. That makes it way, way easier to make granite. So we get subducting plates. So we see granite in places like California and down in the Andes, where we have subduction of plates going under the continents. And that makes it really easy. Right in this region that we call it the back arc, we start getting these silicic rocks. And you can go to the next slide. All I want you to get out of that is we don't have that for the moon, right? We don't have plate tectonics. We don't have water. So we must be getting our granite somewhere else. We have less than 20 of them from the moon. We found them at Apollo's 12, 14, 15, and 16. I've never found it in a lunar meteorite. And they are typically very small. They occur as fragments of soil, like that rock up there on the right. Or they'll be one rock type within a larger breccia. And they are very chemically unique. Again, we're looking at iron and thorium because geologists love those elements. And we see they plot, all I want you to notice is they plot way different than
I have a
everything else.
definition question. So you mentioned the word breccia a couple of times.
Yeah.
Can you explain what that is?
Oh, yeah. So that was the one when we were talking about Apollo 16, and what they found was that the surface was really impacted by meteorite impacts. So for a bad way to say that. What happens is you get multiple rock types that are then pounded on for millennia and then are thrown back together from heat of impact or from compaction, just being pressed down. And so on its surface, a breccia means a rock made up of different rock types that have been pushed back together. On the moon, it's caused from impact.
Thank you.
Mm-hmm. And so just so you can see what a breccia or what a silicic rock looks like in the instrument that I use, this is what it's called, a backscatter electron image. So this is done with an instrument called an electron probe microanalyzer. And what you're seeing is you put your sample in under vacuum, and then you pound it with electrons. And this is looking at the backscattered electrons. So what is bouncing right back? The brighter minerals in this are things that are more dense. They're farther along down the periodic table. And the darker things are less dense. Next. Okay, we also know that we have these silicic rocks from looking at remote sensing. So our images of the moon, both using the chemical data from spacecraft and from just the photography. So we know we have granite-like things, which would be intrusive rocks. So this is kind of where you're getting your countertops, is from when a silicic body is cooled underground. And then we also know these right two images, we see that we have mountains built of this stuff as well. But we're still working out how it forms without this plate tectonics and water. Go to the next slide. And so what we're looking at now is trying to, the community is very focused on it, especially because we are going to land right here in this region. In current launch date is 2029, we are taking a robot to a silicic region for the first time to actually sample these things in place, because none of the Apollo silicic rocks were sampled in place. And so we've been debating the origin of how this formed since the 1970s. And we think we might have a handle on it, where what we would end up with is basalt and granites forming next to each other through a process called bimodal volcanism. And what's happening is you need all those creepy elements. So it comes back to that again, this weird chemistry of the moon. When you get those in rock, it makes it easier to melt, and through lots of the chemistry you can make granite. Yeah.
We have a question online. Arjun, go ahead.
So I was just wondering, is granite a metamorphic rock?
Granite is a volcanic rock. Yep. Or granite is an igneous rock. So you can cool an igneous rock above ground or underground. If it cools underground, it's granite, and if it cools above ground, it's rhyolite.
So you said that there was a lunar meteorite. The lunar granite, it's like an igneous rock, right?
Correct.
Okay, thank you.
All right, you can go to the next slide. All right. So that's just a sampling of the wide variety of lunar science that's still ongoing. We have a healthy community with a lot of scientists who look at these rocks all the time. And we are really starting to ramp up now to prepare for Artemis. So what we've got going on to prepare, go ahead.
Can I ask one question before? So when did the volcanism end? Do we know?
That is such a good question. So the youngest samples that we have are come in just under 3 billion years old. And those are in the lunar meteorites. We've got basalts that are just under 3 billion years old. But by looking at how many craters are on a surface of a given size, we can estimate the age of a surface. And our estimates tell us that we should have volcanism that's closer to 2 billion years old. And then it gets even more complicated because we have these really odd features on the moon. We call them irregular Mare patches. And there's a huge debate going on in the community. Every time we have a conference, we've got someone from one team that comes up and gives us a talk about how they're ancient, like billions of years old. And then we have someone else who comes up and gives us a talk that says, hey, these might be as young as 100 million years old. So we don't quite know exactly the extent, but we are going to one of these craters or one of these irregular Mare patches in the next decade. And we're going to get a date on them. So we will have a better answer. Well, stay tuned. I'll come back in like 8 years. And,
Is that the sorts of things that say Grimaldi? There's a dark spot in the crater Grimaldi that looks like a little bit of Mare.
So Ina is the best example. That's the most famous example. They look like they're bubbled up at the surface. They're very, very odd looking. I think Grimaldi, I think that has Grimaldi, it might have pyroclastic deposits, which would make it really dark. But I can't say for certain off the top of my head.
Is there, when you look at the maps of the moon, it's big Mare and one ocean, and then there's sinuses and there are bays and
yeah.
And eventually you get down to these little spots that sort of come out of nowhere, related to the Mare. And so that isn't necessarily what we're talking about.
No, I'd have to look at an image of what specifically you're talking about, but the irregular Mari patches are generally really small. But we can certainly, after we can pull up a picture of Vainu and talk about it. They're very, very cool looking. The challenge is most people see them inverted, where the high points, most people see as the low points and vice versa. All right, go ahead. So we have transformative science starting now to try and prepare us for living in the lunar environment. I was in no way involved with this, but folks are starting to try, and this was done at University of Florida. This is actual Apollo soils that people are starting to learn to grow plants in. So it's not just the geologists that are interested in the lunar samples. There's a lot of people who have interest in them to learn how to live and work on the environment. Folks are interested in, can we use the lunar sample or lunar soil to make brick, or bricks out of, how can we use it to shield us from radiation? It's an ongoing field of work. Next slide. And we're not done with the Apollo samples yet either. We still have a lot of work going on in these. That is the current curation lab down there on the bottom right. And what has been excitingly happening there is they've been opening samples that have been closed off to the science community since they were collected. Especially in particular, we're talking about an Apollo 17 sample here. They drilled into the surface and they took these core tubes out and sealed them on the lunar surface with the intention that they were not going to be opened for an undetermined amount of time. They wanted to wait until scientific techniques progressed enough. And so what they were doing, they have opened this up and released it to the science community, and we are using it as a dry run for the Artemis program to get everyone ready to analyze samples that have never been looked at before. You can't just look up online the sample number and see what the previous work is, right? You're the first person to look at it. And so it's been a fascinating program, and there's so many lessons learned that are being fed forward in preparation for the Artemis program. What? So looking beyond the Apollo samples, in the future, we're going to have this amazing ability to target exactly where we want to go and get samples. The Apollo program happened so quickly, and there was not a lot of replan time to analyze decades of science on the samples and figure out what outstanding questions do we have and what samples do we need to go get. Well, we've now had over 50 years to think about it, and we know what kind of samples we want to get. And so we're going to be doing a lot of this with Artemis. That's going to return previously return samples from previously unsampled regions, and I'll show you where from in just a moment. So we're going to be looking at resource usability and applying what we know to feed forward to Martian sample return. What? All right, so what's left to sample? On here, this is a completely updated map. Every mission through Shanga 6, which was the last mission to land on the moon and last mission to land on the moon, which landed last June. All of these dots are very large in comparison to the actual size, like, of the sample region, right? So if we went to the moon, or if we on Earth, what is that? I don't know, 20 places about, somewhere in there, 25. If we went to 25 individual locations on the moon and sampled a 100-meter radius, we would absolutely not think that we know everything about Earth, right? The same holds true for the moon. We often hear, been there, done that. Apollo we went 6 times. Why could we possibly need to go back? We have not sampled much of the moon. And a lot of what we did sample was in the prosolar and creep terrain. And not all of these are sample return missions. So the surveyors, those didn't bring back, only 2 of the Lunas brought stuff back. The vast majority of our samples are from what's in the purple, the Apollo missions. And a lot of that is from the prosolar and creep terrain. So we've sampled this chemically anomalous region. Next slide. But we're going toward the south pole of the moon with Artemis. I apologize, these are flipped. So this is the South Pole Aitken Basin, but that's that really huge impact basin on the moon that has anomalous chemistry. So you got to invert for a second here. So this is SPA here, and this is SPA. So it's down in one image. The images on the right toward the basin is down, whereas it's up this way. Blame my colleague. I don't know, the same person made these two images. God blame him. And so what we see is we see some of this anomalous chemistry. Again, elevations in thorium and elevations in iron. So the more red the pixels are, the higher the percentage in the chemistry of those rocks. I want you to look at that Amundsen crater, keep that in your mind, and then switch slides. Okay, here's Amundsen crater. This is the regions that we are selecting from. Go for a minute. And I use we very generously. This is the regions that very fancy, important people are selecting that the crew will go. And I will just study wherever they want me to study. So we are going very, very close to the lunar South Pole. This is the rim of Shackleton crater right there in the middle. That touches the lunar South Pole, or is very near to it. So these are the regions that are currently being considered. So we are going to a region where we are going to have some of that anomalous chemistry that's going to have been brought in, because we are landing right at the edge of that region where we see higher thorium and higher iron. And that's where, so we're landing at the boundary of like the highlands terrain and that anomalous South Pole Aiken Basin terrain. So what we're going to have there is an interesting mix of the chemistry, and people are working hard right now to make estimates of what percent of what type of terrain do we expect, and what kind of samples should we actually be looking for when we're there.
Are they looking for water?
They are. So a lot of these, like Shackleton's a good example. A lot of these regions are in permanent shadow or near permanent shadow. And what happens is volatile species can bounce along the surface of the moon until they land in these deep shadowed in our environments and are frozen. We estimate we have water. How much is yet to be seen. And yeah, so that was the last slide there. It's just, you know, eye candy. We are going back to the moon. We are going soon. And we are going to have many decades of samples to study again.
Thank you very much.
Are you gonna be involved at all in the Europa mission?
I'm not involved in the Europa mission. I have colleagues that are. It's a fascinating mission. I just focus a little closer to home.
So I have a question. So when you're going in to look at a sample for the first time, do you go in with a hypothesis and work against the hypothesis, or do you go in and just say, let's see what's in the surprise box?
That's a great question. And a lot of it kind of depends on what work has already been done, right? So when I was working on, I pointed out the rock, one of the rocks I did my dissertation on, there had been 50 years of science done on this rock. And we wanted to take a fresh look at it, right? But I already knew the background of what people had done on this rock, so I can't go in with a complete no knowledge of anything, right? And so I go in with luckily a lot of what I'm doing is gathering the chemistry of the rocks. And I can't make the chemistry say something that goes for or against a hypothesis. I have to look at the actual data and tell me, see what it's telling me. But then when we're looking at like these new Apollo 17 samples that have just been opened, I was the first person to ever look at them. So I don't know what's in them. And so yeah, I can't have any preconceived notions about what the chemistry might be, because no one's ever analyzed it before. So it kind of depends.
So for the theory of how the moon was formed, I'll pretend like I've read all the stuff I've read. So what would you tell anybody when they say, how did the moon form? Where did it start?
So the moon, for you want me to give my spiel that I would give to?
Yeah, however you want to answer.
So a Mars-sized body named Theia was cruising through our neck of the solar system, and it impacted into Earth. And Earth was still quite a bit gooey at that time, and it was an extremely high energy impact. I mean, it was a Mars-sized body. And so what happened is the material from Theia and from Earth got all mixed up together, and a lot of Theia sunk into Earth, a lot of Earth spun out into space, And there's a period of time where there's this blob going between what would be the moon and what would be Earth. And then a gravitational pull from the two bodies eventually separates them. And they both cool down into the planets we know and love today.
Okay, wow. So how long ago was that, roughly?
4.56 billion, 4 point.
Very early. So
Yeah, it's really early. It's very, very early in solar system history. It's like long before Earth has water or anything, you know, the moon formed not too long after. So 4.5 something. Yeah, exactly.
So you're focused on the science. Are there people like talking about these commercial things and like using the moon as a launch point for bases and mining or anything like that?
Yeah, people are really interested in the mining. So the NASA now has a partnership called the Commercial Lunar Payload Services, where NASA is funding our payloads to go on commercial companies to help kickstart the lunar economy. So like the mission I was talking about in 2029, that's going on a commercial lander. And that you might have heard recently, 2 landers tried to go. Neither of them quite made it, but it was the first time either company had attempted. We missed the moon a lot at first. We shot a lot of satellites past the moon. The fact that someone landed, you know, one of them landed, so it was positive steps. So we've got a long way to go before anyone is using the moon as a base to go somewhere else. We've got a lot of engineering problems to solve, but we are working on the economy. Yeah.
When you're working with the lunar samples themselves, is there anything particularly hazardous? I mean, regolith is basically a lot of shards, isn't it?
Yes, so the regolith has a lot of shards. Luckily, when I work on a sample this big could keep me busy for months, like all the chemistry. I look at things at the micron scale. So I'm more of a hazard to my sample than my sample is to me. But lunar soil is a very, very real hazard. Jack Schmidt says it smells like gunpowder and it's extremely sharp. The crew struggled in between EVAs with the lunar soil that had gotten into the capsule. It was uncomfortable for them. So that is definitely a long-term health hazard. The other one that we have is that we're going to be sampling these permanently shadowed regions, and we're looking for these volatile species. Not all of those are healthy for humans to breathe. So they're thinking a lot about how to protect crew on the return journey from the moon from any leaks that could happen from the samples themselves. So the samples are, you know, on a broad scale, the moon is more hazardous to us than we are to it. But on the fine scale, on my day-to-day, I'm way more problem for my samples.
Thank you. Anybody, any other questions?
is there any, just occurred to me that there are some meteorites on the Earth that came from the moon because they were blasted by meteorites on the Earth. And you showed a collection of those. Is there anything going the other way? I don't suppose we would have found anything on the moon, given the small space that we sampled.
So
that came from Earth and was blasted.
mathematically, yes, there is. We also, like, someone very smart sat down and did the math for all those solar system bodies. We, in theory, have a piece of Venus here. It would be the holy grail to find. But yes, there should be pieces of Earth on the moon, and it will be an incredible find when it's true, because we will then have preserved a piece of Earth likely older than anything we've ever dated. Now, a couple years ago, someone claimed they found it. And the rest of us were real skeptical, and it has pretty much just proved it since. I didn't take part in that, but someone said they did it on one of these, actually on one of the granite samples. But it looks like it's probably not Earth.
But still looking, and it's lots to come.
Yep, absolutely. We're in a whole new era.
One last question online, Michelle.
Yeah, Dr. Valencia, I wanted to ask you if you have any ideas of finding some kind of volatile element that we have never seen before. when you go looking at the permanently shadowed regions on the moon?
I think it's unlikely that we will find any element that's not already on the periodic table. What we might, and we've done some experiments. We intentionally crashed a spacecraft into a permanently shadowed region on the moon. It was called the L-Cross experiment. And then we flew over it with a second spacecraft while we were crashing that one to see what came up in the plume of dust. So we have the spectra from that region, and so we know pretty well what species probably exist. But we might find something we haven't seen before. It's always a possibility on the moon.
All right, thank you so much. That was fantastic.
Yeah.
Folks online, can you see this? Do you see my screen?
Yes.
We do.
See slides again? Okay, so let's move on to the next. I'm just realized I forgot to read your bio, but if we can talk about that later if anybody wants to stay on. Anyways, it's time to talk about the what's out in the shallow sky this month. Jim, do you want to go ahead?
Sure. So last month was our chance at Mercury. Right now, it's heading behind the sun, so it's not a very good target. Click. Venus, you're beginning to catch it in the western sky. It's slowly climbing up. This is not going to be a very good apparition for Venus. It's going to be hanging down very low in the southern sky for most of this time, but you can still catch it on the 5th. In fact, it'll make a nice pairing with the crescent moon. Definitely some photography opportunities there. Next. Mars has finally hit 7 arc seconds in size, but that's still pretty darn small and tedious to try to pick out any details on it. And you'd also have to get up early in the morning to see it. It's a challenge to image it, but people are picking up albedo features. So, and there was a recent dust storm that did not go global, but people did image a dust storm recently. Next. So Jupiter is still an early morning object, but it is rising sooner and sooner each evening. It's heading for an opposition on December the 7th. Always worth kind of, if you're up, breaking out the telescope and taking a look at Jupiter, because there's always a lot going on that planet. And then our final solar system object here is Saturn, which just went through opposition. It's really well placed for observation. The rings are opening up very slightly for the next couple of months. And so an observer's challenge would be, can you make out Cassini's division along the very edge, very tip of those rings?
I'll be doing that.
Hey, Jim,
Yes.
isn't it true that in like 6 months, we're not going to be able to see the rings of Saturn because of the direction that we're facing?
Yeah, basically
as on plane.
Yeah, as Saturn comes to its equinox, the rings, which are so incredibly thin, will basically disappear. Part of the problem is, though, in 6 months, it's going to be near solar conjunction, so we really won't see it that well. But yeah, the rings are going to be very thin for the next, like, 18 months, probably.
They're starting to tilt up, right?
They're opening very slightly, but then after the first of the year, they're going to close up even further than they were this summer.
Right.
There's a motion of your.
Okay.
So probably the big news is comet, and I'm not even going to try to pronounce it, Tsuchinshan C2023A3. This guy has been eagerly awaited. It's going to reach perihelion next week, and then it'll hit perigee, closest point to Earth, a few weeks later on October 12th. In between those two times, it ducks in between us and the sun, so we will kind of lose it for a period there. Next click. Currently, people that are able to catch it, it's a very low and early morning object. The people in the southern hemisphere right now have a better opportunity to see it. It's about 5th magnitude, and it's in the constellation Sextans, which is like below Leo. Next. So this is towards the end of the month. If you get up early, you'll have a chance to see it looking east. You can see that it doesn't get very high, up at all. That's only about 30 minutes before sunrise, so the sky's starting to bright. But you can possibly with binoculars, and especially using the moon as a guide on the 30th or October 1st, that'll be a really good opportunity to get your first look at it, perhaps. Next click. And then after it goes past us, we will get an opportunity in the evening sky, which will be a lot more convenient. So here's a simulated view of it on the 17th. It could get up to third or second magnitude. Some of the more optimistic people are saying even brighter. But this would definitely be another good opportunity in mid-October, right before our next meeting, to get out there and see if you can pick up this comet. And like the famous saying is, comets are like cats. They've got tails and do exactly what they want. So it could turn out to be a really nice comet, or it could end up being like maybe only fourth or fifth magnitude and not really even naked eye from around here. But let's keep our fingers crossed and hope for a good show out of this one.
Jim, though, so if we go out to Carr's Mill, which has that perfect view of that area.
The
We
east.
can see the whole thing. And we take the 5-inch refractor, we put the night vision device on it. Just jump out, right? It should be great.
It should, yeah. Yeah.
All
And I
right.
think that,
Sorry, go ahead.
I think that's it. Yeah, that was it.
Yeah. Okay, thank you so much. That was awesome. And now we have a special feature we don't normally do, but Arjun has visited an observatory and would like to give us a little trip report and share what it is that he saw. So Arjun, you want to take it away?
Yeah, sure, I will. Okay. Thank you so much for introducing me. So my name is Arjun, and I am a freshman in high school. So this summer, as some of you may know, I took a trip to India, and I also took a trip to the Vainu Observatory in southern India. So this is basically just about what the observatory is, what they're doing there, and then in the end, what I thought of it and what was there. Next slide, please. All right, so this is an introduction about the observatory. The Bappu Observatory was founded around in the 1960s by Bappu, who is a leader and father of Indian astronomy. Bappu has made many discoveries, but some of the discoveries that he made were a comet, an asteroid, and has an effect named after him, which is with another scientist. This is called the Wilson-Bappu effect. Next slide, please. So this is the observatory campus. When I went on the observatory campus, I saw 4 telescopes. I wasn't able to find a picture of one of them, but these are the 3 main ones. So the Vainu Bappu telescope, which is a 3.2 meter Ritchie creation telescope. The Carl Zeiss telescope, which is a 1 meter Ritchie creation telescope. There is also a 15-inch refractor telescope and a 30-inch reflector. So each of these telescopes have a lot of diverse equipment on them, and they are fitted for the needs of the astronomers who are going to be working there. So pretty much this is a all-in-one observatory campus. Sadly, these observatories do not share their data to the public because they were founded by a private institution. Next slide, please. So here are some of the discoveries that the Vainu Bappu Observatory has made, including the discovery of rings around Saturn, the discovery of 6 new asteroids, and the discovery of a thin atmosphere around Ganymede. And alongside with this, there is a lot of research that is currently ongoing in that observatory, which is things such as the ultraflow dispersion spectroscopy of stars and the Large Magellanic Cluster, observations of many, many things like stars, clusters, supernovae, blazars, galaxies, gamma ray fields, and so much more. Next slide, please. So if you want to observe all of that, you need to have the right instruments to observe it. So the Vainu Bappu Observatory has been equipped with many different instruments, and some of them are imaging cameras, HAL spectrographs, medium resolution spectropolarimeters, medium resolution spectrographs, and visual band, narrowband, and broadband filters. Next slide, please. So the location of this observatory is interesting. It is located on the Javadi Hills in India, which is a fairly serene and calm hillside. It's fairly high up, and the reason that they chose this location is because it's clear for a majority of the year, over 286 days a year. And it's also a Bortle 5. So since India is a really populated place, it's fairly hard to find really dark skies. So a Bortle 5 is fairly decent for the location of the telescope. It's not ideal, but yeah, it's still a really great place for this telescope to be located. And this campus hosts the second largest telescope in Asia, which is the 2.3 meter Vainu Bappu Observatory. Next slide, please.
Do you know how high it is? How the elevation?
I'm not sure of that. These hills have been fairly unmapped, but I would guess it's around 500 meters. I'll search that up and I'll get back to you.
How about wildlife? Is the area?
All right, I'll get to that.
Oh, okay, sure.
Yeah. And next slide, please. All right, so this is where I share my thoughts. So there's a small village beneath the hill, and we had to make our way through this snaking, winding path. And at the top of the mountain, there's like falls and rivers. So the ecosystem is really diverse. There were a lot of mountain monkeys that greeted us by the path, and they were really intent on stealing the food. But other than that, there were like birds, insects, a lot of them. And there were a lot of like vegetation and stuff. The area is pretty well maintained. They mowed the lawn and everything. But on the side of the roads, you can see that like the forest is pretty dense and deep. And answering Mr. Victor's question, the observatory is 3,800 feet up.
Okay. Thanks.
Yeah. And I have one last slide after this. So these are some of the pictures that I took there. So the first one is just underneath the telescope. The telescope is really huge. The dome is also really huge. I'm not really sure how I could put it into context, but it was really big. I would say about like 20 feet in diameter, the whole observatory. The next picture is the photo of astronomer Vainu Bappu. He was the one who founded this observatory. The one after that is just a swing that we randomly found. I think the area is like a park. So there were like a bunch of trees that you could like climb on and swings that you could swing on. This particular swing went really far back. It's kind of scary to be on. The image after that was a photo of a mirror, which is similar to what they have on the telescope. It's 2.3 meters and it's fairly big. And I think if this mirror was actually inside the telescope, the images wouldn't be really good. The mirror was really dirty, but it gave like a good idea of how big it was. Then the rest of the photos are just along the paths that we went. It's a pretty long walk up to the observatory. And at the end, once you finish the path, that's where the big telescope is. Alongside, while you're walking, there's like forest, and occasionally you might see like the 1 meter telescope and 15-inch reflector. And I didn't include these photos in here, but they're constructing a new telescope. And that was pretty interesting. I think that telescope might be more modernized, but that's my thought. Next slide. All right, so I'd like to thank you for listening. And if you guys would like to hear a little more about the observatory, you guys can go to my channel, Arjun, Meenashi, Sundar. Just type that in on YouTube. And I think the first video that I posted, like the latest video that I posted, is of the Vainu Bappu Observatory. So don't forget to smash the like button and subscribe to my channel.
Thanks, Arjun. Do we have any questions?
Great presentation, Arjun. Thank you.
Yeah, that was awesome. I noticed Harini was not on the swing. It was you. Did Harini go too?
I think we had to do a lot of convincing to get Harini on the swing because it's really massive. It's pretty tall.
Yeah. Okay, well, thank you for that. That was really cool.
Yeah.
I want to ask you some more about it, like what this, you said something about they don't, I mean, they have scientists who publish their findings. But when you said they didn't share with the public, you mean like you can't go online and see their data like you would on NASA? Is that what you mean?
No, I actually asked them about this after they were done with their presentation over there. They told me that the observatory was founded by a private institution. The land was originally owned by someone else, and then the astronomer who bought it, I think it's the Tata Institute. They bought it and then they built the observatory on it. And so most of the scientists who work on it, they're international, but the data is used for like private research.
Okay, interesting. Okay, so now we get to our members' astro photos and images. So first is Rich Friedrich. Are you on? Okay, he is. Can you guys see that? Are the lights? Maybe we could turn the lights off. So this is I don't know the details, but Rich was telling me that this was taken with an iPhone at a star party. So I thought that was pretty cool that he was able to capture that pretty good amount of Milky Way there. And then Rich, are you on? Richard?
No.
So if you guys think this is a photograph, I'll let you know that this is a drawing. So this is Rich looking through his 6-inch refractor and making a drawing. So I think this is really quite amazing. The details there on the bottom. Jim, are you still on?
Yeah, so just a shot of Jupiter towards the end of last month, picked up a couple neat features. The great red spot still hanging in there, it's with us. The white dots below it there are some long enduring anticyclones. And then we're seeing a lot of these hotspots, blue festoons, whatever you want to call them. There was a neat article in this month's November Sky and Telescope about these things, North Equatorial dark formations, and they are like really prominent. You can really catch those visually, not just photographically when you're observing it.
These guys here?
Yep, they're actually areas of the planet, as you would read in the article, that are peering further down deeper into Jupiter. And the reason is kind of like bluish gray is because of Rayleigh scattering, just like our blue sky here.
Huh. Interesting. Thanks for that. And another one of yours here?
Yep. Same morning, the moon was kind of waning, crescent, and Plato was looking really awesome. So I just grabbed this shot of it.
That is fantastic.
Yeah, one of the nicest craters to observe there.
Yeah, that's beautiful. I don't see any astronaut footprints though.
No, I need a larger aperture.
Yeah. Steve, are you on?
Yes. Yes. Yeah, because of the orientation of the orbits of the satellites, it's now possible to catch a transit of Saturn satellites. And of course, Titan would be the obvious one to look for, and I was all prepared for that, but naturally it was cloudy that night. But I was able to get Rhea, and you can't really see the moon because Saturn's surface is pretty much the same color as the moon, but you can see the shadow, and you can see that it moved across the planet in that hour that I was taking the pictures. This doesn't happen very often, of course, because everything has to be tilted just the right way. and it has to be clear. And you have to, doesn't take very long, so it has to happen during a time that you're out there. Rhea is the next biggest satellite after Titan. Dione is the next one, and beyond that, you probably won't be able to see them because they're too small. But you need to keep watching, because this will be happening off and on for a while, and it's a unique circumstance.
Yeah, right.
Hey, Steve, what aperture did you use?
This is with my 14-inch Celestron with a
Very nice.
Zero 2600 MC camera.
Very nice.
Yeah.
This is
And this was just a set of the images just to show what's happening to Saturn over the years, from the first one I could find in my archive in 2005 up until now. I do have some pictures from the 1950s, but I can't find them. And of course, they're film pictures. They're on.
I have a question for you guys. I have a Celestron 8 SE, and I'm looking to get a camera for it. If you could send some recommendations to TO.
Let's talk right after the meeting.
Oh, okay.
Yeah, that would be, there's definitely, and you can actually, probably better to post an inquiry on the HAL, on the
website,
not the website, but on the Google Groups chat.
Okay.
Then, yeah.
I have a couple of Zero cameras. The first one I got was the 224, which is really a planetary camera, but I found that this 2600 does just as good a job and is more versatile. So I'm using the 224 as a guider now.
All right, great, thank you. And Harini, are you on?
Yes, I am on.
So these are both Saturn. Looks like different exposures on your C star.
Yeah. So the first one on the left is Saturn. You can't really see it, but then it's the dot in the middle. I couldn't get really well of it. It was relatively tiny, but then if you zoom in a little bit, then you can kind of see the rings.
Right.
And then the one on the right, is also Saturn, and then it has a 1 minute exposure. This one is actually stacked.
Right. So sometimes people try to get the moons by doing the long exposure, and then they superimpose that with the short exposure to get the rings and the detail on the planet. But that's cool. But I like your next ones. These other two that you sent in are really nice. Can you talk about them for a second?
Okay, so the one on the left is the Andromeda Galaxy. I took it for 46 minutes. It's in the constellation Andromeda, and its apparent magnitude is 3.1. It's also 2 million light years away, and Andromeda is a bared spiral galaxy.
Right.
And then the one on the right, it's the Veil Nebula, which I took for 36 minutes, and its distance is 2,100 light years away, and it's in the constellation Cygnus. It's also in the Cygnus loop, a supernova remnant, and the apparent magnitude is 7. And also the star that made the Veil Nebula was 20 times larger than our own sun.
Awesome. I remember that was this was taken at one of the impromptu star parties, right?
Yeah, these were taken on an impromptu star party.
From
But
Alpha
then,
Ridge.
yeah, but then the other two, the Saturn, we went to the Observe the Moon night and we took it over there.
At NASA.
Yeah.
Great, and got in Greenbelt, right? Okay, thank you so much. Next we have another Michael. Are you on?
Yeah, hi, Victor and everybody. So this image here I took with my C-Star as well. Looks like, I don't know, it seems to vary what it looks like depending what screen it's on. But this was about 7 hours of stacked data for my C-Star in my backyard with both M81, M82 in the same image.
Pretty amazing, actually, that you can get this with that little tiny aperture. That's quite nice.
Yep.
Thank you. And I see you put something in the chat too. So I'll discuss that after with regards to your 8SE. Okay, and then the next one is going to blind us all. Are you on, Gene?
Yep, I'm here.
So this is Perseus, huh?
Well, the Perseus galaxy cluster, and the brightest galaxy in there is, of the two bright ones above center, the top one is NGC 1275. Yeah, that one. And if you zoom in, well, you don't have to zoom in on, but if you zoom in on it, there's actually a galaxy in front of a spiral in front of NGC 1275, and you can just see the little arms sticking out.
Okay.
Like to the upper right and upper left and the lower right. If you look at a Hubble photo, you can.
I'm afraid I'm gonna screw up the presentation if I try to zoom.
No, I don't want you to zoom, but anyhow. So
it's very nice.
Yeah, and these are like a little over 200 million light years away, and there's galaxies all over. The more you look, the more galaxies you see.
Yeah, awesome. This is with your SCT?
No, it's a Newtonian, a 10-inch.
Right. Oh, of course, like you can see the
yeah, you can see the diffraction spikes.
Yeah, the diffraction spikes, right. Thanks. And then Gene, you have another one, which is, if I can get my mouse to come over where I can see it. This is I like your naming convention here, the dumbbell, or
everybody calls M27 known as the dumbbell, but when you take it really deep exposure, you get these oxygen 3 wings on it. It looks to me like a butterfly.
Yeah, that is about as deep as a photo of that as I've ever seen. That's awesome. All right, and then I think last but not least, we've got Jim. Are you on, Jim Johnson? He could be on, but he maybe fell asleep last time he fell asleep. I'm just giving you a hard time if you're listening, Jim. But this is just a beautiful shot. I love this photo, and the display projector here in the room is not doing it justice. It's just an amazing shot. So, and I don't know the details, but I think that in the title of the name of the photo, he had RGB03 and HAL. They combined a whole bunch of different images. So gorgeous shot. So that is everything.
Victor.
Yes.
This is Joe Novatka.
Hi.
I sent you one of my pictures. Maybe it didn't make it to you before the meeting. I sent it during the meeting.
Yeah, no, I don't think I can get to it right now. Maybe we'll show it next month.
That's fine.
Yeah. All right. Well, thank you so much, everybody online and in the room, for coming. And I'd like to ask to say thank you also to our speaker. That was just really, really cool. I enjoyed that so much. And I really do wish that we would have been able to talk to you before observing the moon night, because
Okay. Well, for next year.
yeah, I'm going to stop the recording.